Hi, I'm Ryan, and I collaborated with Jen Chung and my advisor, Jeff Hollinger, from Oregon State University in the Robotic Decision-Making Laboratory. And this work is risk-aware graph search, which is a search algorithm meant to incorporate uncertainty in edge costs and path planning. So the high-level kind of motivation that we were looking at here is trying to incorporate environmental knowledge with low-level sensor information. So as you can imagine, a quadcopter flying in a forest, you have a LiDAR, you get to use that sensor information to avoid obstacles, as we just saw in the talk. We can use that kind of local information, but what if we had high-level information as well, perhaps satellite data, to better plan through the forest and find paths through less dense areas and have a stronger and more robust planning method. Another example would be, especially people that live in San Francisco can imagine driving to work can range from 30 minutes to 3 hours, depending on if there's a traffic jam or someone got in a car accident on the 880. So this is kind of looking at those scenarios where there's a lot of variability in traversal cost. And so this domain falls into the Canadian traveler problem, which was brought up earlier. What this kind of focuses on is the uncertainty in the moving from one vertex to another vertex. So in Canada, they get a lot of snow, especially in the winter. I know we have a lot of Canadians out there that are probably dealing with that right now. But when you're out on the roads and you're driving, you're not certain if the path to the mountains is going to be clear. And so you're going to get there, and then you're going to realize, crap, I have to turn around and go back and find an alternative route, or I have to go the long way around the mountain pass. So this is kind of the general domain that we're looking at. And then the extension of this is the stochastic shortest path problem. So this is where we're actually modeling the probability of that path being blocked or open. And so we're going to kind of tweak this just a little bit for our purposes, and we're going to add local information being available. So sensors for us, if we're driving in this example, our eyes, we can visually see the weather conditions and estimate how the terrain will be in our local area. But we'll have kind of a model of what the farther roads conditions would be. So we're not exactly sure, but maybe we have a probabilistic kind of guess of what these are going to look like. And so to address this problem, we propose risk-aware graph search. And what this is doing is it's searching through a graph to find a goal over these over normal distributions of edge costs. And we're trying to find a path with the least amount of risk. And so you can see here, this is kind of a high-level example to kind of give you an idea of how this would differ from some more deterministic search algorithms like A*, where you would search over the expected cost. So in this example, A* is picking the low mean path, and instead of incorporating the availability of alternative routes and the option of having lower cost paths available because of those options. So RAGS takes into account lower mean, trade-offs between child paths and lower mean. And so the way we actually are going to quantify this risk is by determining what the probability is that a lower cost path will be available at each neighboring vertex. So if you have vertex A, vertex B, each neighboring vertex will have a number of child paths that are going to go to the goal, and these are going to have an estimate of what this cost would be to travel to that goal. And we're going to integrate over all those child paths in order to identify the probability that the lowest cost path in set A is lower than lowest cost path in set B. So that's a bit confusing, but it becomes a relationship between the mean, the variance, and the number of paths. And this allows us to do local ordering, so we can determine which neighboring node would be the ideal node to continue along in order to reduce the risk of a high cost path. All right, so in order to navigate through this graph, we're gonna have to actually bound the paths that we're looking at, right? Because it's gonna be intractable if we're just looking at a giant graph with cyclical paths and wide detours, right? So what we're going to do here is we're actually going to bound the nodes. Sorry, we're going to bound the paths and call them dominated if they have both a worse mean and variance, right? So if they perform worse in both categories, we consider this dominated, and we don't expand this node or look as a viable path option. Okay, so in order to do this, we set up a simulation where we randomly generate graphs and we sample the edge costs from distributions between 0 and 100, and we're trying to navigate through the graph, and we're going to compare this against A star, sampled A star, and greedy. So sampled A star is actually just going to randomly draw a value from each probability and search the graph some set number of times, and the path that ends up getting chosen the most will be the final path. And greedy will just take the local data into account and follow the lowest cost path. All right, so this video is going to kind of give you an idea. So it's a little confusing to explain, but what we're going to do for the simulation is we're going to generate a PRM, and then we're going to go ahead and we're going to prune the edges for non-dominated paths. And the way we're going to do that, right, is by looking at domination and bound it, and then we're going to traverse the graph with risk-aware planning, where we're comparing those neighbor nodes. So we have the path set, and then we compare each neighboring nodes to get our final path. And so what this gives us is a tighter dispersion in our final results. So what we're looking at is A star and sampled A star and even greedy have these outliers and are spread kind of thin over the optimal path. So on the y-axis here, this is the percentage above the optimal path for each simulation, for each run. And so what you see is that, with A star and sampled A star and greedy, you're looking at these high cost paths and these outliers. And what we're trying to do is we're trying to bound this and bring it down and reduce the likelihood of getting one of these high cost outliers, right? So if you're up in Canada and if you're driving an ambulance, it's really important that you get there on time and that it's not going to take 8 hours instead of 3, right? It might be okay if it takes 4, but 8 hours is not acceptable. So we're really trying to look at reducing these kind of outliers. And so for our experiment, what we did is we took a data set of satellite imagery and we filtered out tree clusters, man-made structures, and we kind of took them at different kind of resolution levels. And then we filtered it and we extracted the obstacles, and you can kind of see an image here where the intensity of the pixel kind of demonstrates the likelihood of it being an obstacle. And so we use that to kind of estimate the traversal cost. So what we're kind of trying to do is get some kind of idea of the terrain traversability, right? So we use the intensity to generate these probability estimations, and then we ran that through our data set, and we got these results. And so again, what you're seeing is the quartile for A star is a lot higher than RAGs, and you're getting those outliers. And sampled A star, while the dispersion is a lot tighter, the reason that we have this result in our paper is that you can see this super high outlier here, right? So it's if high cost is extremely important in your application. This is where you're going to get the benefit of our algorithm. So you're seeing that RAGs really limits that risk. Okay, so here's kind of an example of what that would look like. So the blue path here is RAGs, and the A star is the red path. And then the hindsight optimal is what would have been the best path if we had all of the information perfectly available after we'd already executed, right? So that's going to be the black path. So what A star does is it finds this narrow track through the forest that looks like it's a good path. So it looks like a viable path, but as you can see, it goes right through the forest, and there's a high likelihood that there's going to be a branch or if anything comes across that path, if you can't quite make it, you're stuck in this dense obstacle, right? So what RAGs does is it goes around and it finds a sparser area to navigate through. Okay, so it takes advantage of the open area and all the available paths it can go through by going around the obstacle. Okay, so the benefit of using our algorithm is that it provides robustness, right? So if you're really aware of your final path costs and you can't risk having a high cost, that's where you're going to see the benefit. So traditional search methods like A star and sampled A star and even greedy, you're going to get those outliers. That's what you're risking. And so by incorporating the uncertainty from the real world, we can actually better traverse these paths, right? So if we guess what it looks like, if we can provide any kind of information to our search algorithms, we're gonna actually be able to navigate more robustly. And we see that RAGs actually performs better on well-connected graphs with high uncertainty. So if we really don't know what it is. And so it looks like I'm almost out of time, but here's the dirty laundry. Normal distributions aren't going to be perfect for every scenario, and we realize that, but it's a good starting point. And so we feel like this can be tweaked a little bit if you have a different distribution that you would desire. And then the algorithm is only as good as the world model, right? So because we're making up these probability distributions of what we expect the traversal cost to be of the terrain traversability, it's only going to be as good as we make it. And then this is kind of the argument that is always hard to make, is something's better than A star or sampled A star, and I get that. But if it's really important to reduce those outliers for you, then this is where you're going to get those benefits. So thank you.
Thank you. Okay, Kristen, there we go. Yep.
So
Loud.
your weights are Gaussians, right? So they can also have negative. So every cycle in your graph basically can have non-zero probability of having negative weight. So in your paper,
Yeah, so one of the shortcuts that we have to make in order for this to work is that you're not going to have a negative cost, right? And so what ended up working for our simulation for our experiments and for actual implementation is you're going to have your expected cost, maybe say it's like 100, and if you're within 3 standard deviations of that, it's fine, right? So this is also why I brought up normal distributions aren't always going to be the ideal situation for every case. This is kind of the basic framework that we're starting with, but there's like logarithmic or
my
Poisson.
question is actually just going towards that. So if you think about processes surveillance missions, do you feel like this method can be extended to do cycles as well, not just paths?
I see. So incorporating it so it can actually do cycles or okay. Yeah, we avoid that mostly from our bounding, and the reason we do that is because the tractability of the problem increases greatly. I mean, we're already considering all the paths available. So by doing the bounding, we reduce that a lot. But if we were to consider, cyclical paths and everything, then the computation would get extremely large and be hard to compete with some of these other algorithms. So.
Any more questions? Oh, okay, keep going.
Second one would be more about if your distributions were static but time varying, you wouldn't know beforehand how they vary. So you would probably take your algorithm and apply it to each one in time, like in any time fashion. But let's say you have some kind of constraint that tells you that the variation is slow. You don't know what it is, but it's slow. Would you maybe minimize the number of sweeps that you need to do in the initial part of your algorithm? Could it make it somewhat incremental?
So from what I understand the question, if we were trying to navigate this with time varying distributions and it was slow enough, how would we approach it? Is that right? So the time varying aspect is really interesting. It's actually something we wanted to continue on this work with. If it's slow enough, I don't think it really factors in if the speed, like how fast that it's time varying, right? So just adding in that extra variable, it doesn't really affect our algorithm because as we go, we are kind of comparing the probability distributions. The big restriction would be any of the paths that we had previously kind of disregarded. We would have to reconsider because with time varying, they might now be a viable path, and some of the other paths that we had originally thought as one of kind of the better options are no longer viable. Right.
Oh, one last question.
Leslie,
right?
we should.
Oh, we're done. Okay, sorry. Overruled. We're done. Thank you.